Today I'm going to be talking about unbiased estimators. So the definition of an unbiased estimator is in blue and highlighted, and it says an estimator which you can obtain in a variety of methods. The two most common are called maximum likelihood or method of moments estimation. But however you obtain an estimator, it's unbiased if its expected value is the true parameter theta. So we're calling theta hat the estimator and theta the true parameter. What this says in words is that on average, the average value of this estimator is the true parameter, and that's a nice property to have. Various books talk about nice properties of estimators. One nice property of an estimator, in addition to being unbiased, is to have minimum variance. And I might mention that a little bit later. So in this example here, we have a random sample of data which is typically independent and identically distributed. It's unlikely that in a random sample that one observation affects the other, and it's identically distributed if they're all come from the same population or have the same underlying process. Okay, so in this case, the sample average x bar is an unbiased estimate for the population mean, and here I'm going to prove it. Okay, all we have to do to prove that the estimator x bar is unbiased is to calculate its expected value. Well, the definition of the average just says add up all the values and divide by n. So taking properties of expected values, this would mean that this is 1 over n times the expected value of each individual observation. Now, the expected value of each individual observation, they each have mean mu, and that is the expected value. Now, since we're adding mu n times and dividing by it, this is going to be 1 over n times n mu, and that is mu, so it's unbiased. Now, this is just a little bit extra, but I'm going to show you a few web pages talking about unbiased estimators. So we're going to first talk about this one. This has different terminology than what we have, but if you're hitting the bullseye, if all the darts are in the middle here, the high accuracy, high precision, if you're hitting the bullseye, you are unbiased. So there's another dartboard here in which you're hitting the bullseye. It's high accuracy, low precision. But you can see here it's spread out. Having a higher spread, that's a property of having higher variance with this third to the right. So high accuracy, low precision, because it has more spread, it's less precise. We would obviously prefer to hit the bullseye in the middle every single time. That's high accuracy, high precision. That would mean you want the lowest variance possible and you want to be unbiased. Now, the other two graphs, this low accuracy, high precision, low accuracy means that you're not unbiased here. You're not hitting your target. You're not getting the true population parameter. The high precision means that the estimates are highly clumped together. It's low variance. So you're able to tell that there is a lot of that you're consistently missing your target. Now there's low accuracy, low precision. You're not hitting your target, and you have a high variation. So this would be a high variance estimator that's biased. Okay, so just to show you a few other people talking about biased and unbiased estimate, here's your actual value A. You have an estimate and it's hitting it. It's hitting it in that its most common outcome is the actual value. A biased estimator, the actual value A is missed here by the most common outcome. So that's a biased estimator. Okay. So a couple of different people talking about biased and unbiased estimators, and going back to the direct definition that you will see in this course, which is here. Okay, so that was just a little bit of discussion and example of biased and unbiased estimators. And by the way, it's biased. An estimator is biased if the expected value of theta hat does not equal the actual parameter. Okay, so just if this condition here is not met. Thank you very much.